welcome to my YouTube channel. Today I'll be talking about biological logic gates, what they are and how they work, while providing some concrete examples and some fun analogies. You can think of logic gates as the basic building blocks of electronic or biological circuits. The relationship between the input and the output depends on certain logic. There are logic gates, such as a NOR gate, an OR gate, a NOT gate, an AND gate, and so much more. Some circuits only have a couple of them, whereas microprocessors can have millions of logic gates on a single chip. Synthetic biological circuits use a series of logical functions to perform complex tasks. Whether biological or electronic, logic gates sense specific signals and respond to them in a predetermined way. When both conditions are fulfilled, an output is produced. In electronic circuits, electric currents act as inputs, 0 when the electric current is turned off, and 1 when it is turned on. In synthetic biological circuits, components that control gene expression act as inputs. An example with this would be the fluorescence of the GFP protein when all conditions are met. During gene expression, the RNA polymerase is required for transcription, but it can't bind with the promoter if the repressor is in the way. In this case, the repressor acts as an input and the protein as an output. When the repressor is there, the protein can't be produced, and when the repressor is absent, protein can be produced. So the bubble is the promoter, and my hand, acting as the RNA polymerase, wants to bind to it to produce a protein. I know protein has been produced if the value of this dye changes. I can press it, and we could say a protein has been produced. However, when a repressor is on top of it, there's no way for the RNA polymerase to bind to the bubble and change the value of the dye and produce a new protein. When the repressor is present, no protein is produced. However, when the repressor is removed and the RNA polymerase can bind to the promoter, a protein is produced. And that is a biological circuit with a NOT gate. Another logic function that exists in cells would be the presence of activators when RNA polymerase tries to bind with the promoter. If the activator isn't there, the RNA polymerase can't bind to the promoter and protein isn't produced. An activator, which is represented by scrunchie this time, is required for the proper positioning of the RNA polymerase on the promoter. The RNA polymerase won't know where to bind unless the activator is present. If I put the activator on the promoter, the RNA polymerase will be able to bind to it, position itself properly, and produce a protein. If you caught on to that, you'd know that this actually represents an AND gate. Biological organisms don't work on binary logic, which makes these circuits more complicated. Let's take brewer's yeast, which has both a galactose network and a glucose network to import, sense, and metabolize the respective sugars. Because this yeast prefers glucose, when there are high concentrations of it, the galactose network is shut off. However, when there are low concentrations of glucose, the galactose network is still partially on. So it's not only a matter of whether the glucose or galactose is present or not, it also depends on the concentrations. Thanks for watching. I hope you read my article on synthetic biological circuits and you learn a thing or two. Stay tuned for next week's video, and in the meantime, subscribe to my newsletter. Bye! Thanks for watching.